Okay, so in 1675, Newton sent a letter to Robert Hooke saying, "If I have seen further, it is by standing on the shoulders of giants." And this is really the ethos of science, building upon other people's work and ideas, that sort of reuse and reproducibility. What is interesting about this is that Newton and Hooke were rivals, and Newton actually meant that as a sarcastic comment, a dig about Hooke's slight build. And this is an interesting tidbit of information, but it also points to the dissonance between the collective and the individualistic enterprise of science. And these two goals are often not in harmony and illustrate some of the difficulties at play in science between some of the personal ambitions that someone in a field might have versus the collective goals of a community, and ultimately the profound societal impacts of scientific research. In these expanding circles of scientific discovery, there are questions to ask on how you work and how your work can be reused and shared with others, and how that developments and those sort of communities are aligned, both in terms of their incentives and the tools that we use. So when we look forward from 1666 to another discovery about gravity 350 years later, this is the LIGO detector, which is listening for gravitational waves with precision lasers. And in 2016, the detector heard this faint chirp, which was gravitational waves from a collision of two black holes. And in 2017, this won the Nobel Prize as the first observation of gravitational waves using sophisticated data collection, massive teams of people coming together and collaborating, software behind the scenes processing to actually make that new observation and ultimately a new discovery. And if we look to how these are communicated from 1666 to 2016, the major innovation is two columns. And so when we think about what is actually happening next, like how do we want to evolve our science communication to actually make use and reinforce the community's collaboration, software, data, reproducibility, all of these things that is the work behind the work and behind these discoveries. It is not just about removing this PDF document, but really incorporating the process of science into how we communicate research. One community that is really thinking about this deeply is the Force 11 community. And this stands for the Future of Research Communication and e-scholarship. And if you haven't heard of the community, you've probably heard of many of the things that have come out of this community through their working groups, is they've influenced and stewarded ideas about the FAIR data principles, findable, accessible, interoperable, reproducibility, as well as things like software citation principles, and many more ideas. One of their pieces of literature that they put out was their original manifesto, which left some guidepost recommendations that I want to explore today. And the sort of trifecta of three things that they were talking about in this manifesto was giving data and software and workflows a sort of first-class perspective in the research objects that we publish, as well as rethinking the unit and form of scholarly publications, so not just that static PDF document, but maybe smaller pieces or very different ways to sort of interact with research. And ultimately developing better tools and technology that support the entire scholarly research lifecycle that potentially starts in that data and software that we're talking about a lot in the pyOpenSci communities and exists all the way through that entire scholarly lifecycle. So I want to bring some of my own experiences in trying to bring these recommendations to life in my own career. And the first day of my structural geology class in undergrad, the instructor told us that structural geology was hard because it required 3D visualization skills that some or maybe even most of the class would struggle with. And what was frustrating about this was that he was right. The grades showed this clear bimodal distribution of students who just got it, and the rest of the class who was struggling to keep up. And as an undergrad student just being introduced to 3D visualization tools in MATLAB, I was learning to program, and I could see ways to change this and sort of change the way that this was being communicated so that a learner could add beds, and tilting events and folding events, and actually see things when they're adding them, like unconformities and dikes and faulting events and more folding events potentially, until you get to the end of this very complex process. But you can interrogate this model, you can change it, you can spin it around, and you can engage with these models in completely different ways. And the feedback that I got from releasing these tools was quite profound to me. This was the first tool that I had ever released, and it hit this chord with students. So as a student struggling to grasp 3D structures, this is the greatest tool I've ever seen. I will owe most of my success in structural geology to this, so thank you. And this, both encouraging me to go down this road, sort of introducing new tools, I think it's really striking at the top of changing that form of how people interact with ideas and infusing software and computational models into the way that we learn, so that we can enhance learning and allow students to discover ideas on their own and really to interact with them themselves. So those visualization tools that I built for my peers in my undergraduate class in MATLAB, I eventually put those onto the web, and that is when they sort of got picked up by over 1 million geoscience students worldwide. And that was while I was starting my own PhD. And my PhD was the intersection between hydrogeology, geophysics, and geology, and trying to identify ways in which these disciplines could work together in a more quantitative way. And of course, as in almost all fields of science, we were working with large-scale data, we were using software to process that data, we were creating optimization routines, using tools like SciPy and NumPy to come up with better models for the subsurface to estimate parameters. And we were also writing stories about our discoveries and efforts as scientific papers. And in all of this, I was building upon the work that my lab groups had done over the many, many decades. And as tends to happen in a PhD program, my colleagues began to graduate. And I started to discover that building upon their work was much harder when I wasn't able to go down the hall and ask them where the data was, or their software wasn't quite as well documented or reproducible or extensible as I thought. And all that we were left with at the end of this was sort of the story of the papers that were published. And so this intersection between software, data, and story is really where I was sort of stewing on these things and starting to come up with some of the ideas around Curvenote, which I started in 2019 with Steve Purvis. And because I believe that science deserves better than a PDF, and scientists deserve better tools to communicate their work that incorporates software and data at the heart of the medium. And so at Curvenote, we develop all sorts of tools that allow you to have collaborative writing experiences where you have integrations to citations and really pulling some of the scientific work together, where you can directly reference things like figures and have those show up in comments on the side, and ways to integrate to the data science ecosystem as well. So on the left-hand side, there's Jupyter environment starting, and you can copy a link to a data science visualization and paste it into the way that you're authoring that research. And our main focus at the moment is ensuring that the way that we publish can take advantage of some of these new capabilities, the way that scientists actually share their work, which is today largely in those PDF documents. So in 2021, funded in part by the Sloan Foundation, Curvenote open sourced many of these tools to help build and help reinforce the MyST Markdown ecosystem. So MyST, which stands for Markedly Structured Text, is a markup language that builds on top of the Common Mark standard for structured text that can connect to data and computation and includes sort of the specification for that language, as well as the tools to work with it, create websites, create PDFs, and the diverse community around that uses and supports those tools. So throughout MyST's lifetime, it has supported so far, based on the GitHub dependency graph, over 14,318 books as of this morning. It is, in terms of comparing the active documentation ecosystem and the Python ecosystem. Over 13 to 15% of that ecosystem is powered by some of the MyST Markdown tools. And it is part of the Jupyter ecosystem as of about 4 months ago under the brand of Jupyter Book. And there are many, many contributors for this. And so I want to go through some of the guiding principles and superpowers behind the MyST and the Jupyter Book ecosystem, and then dive into some case studies as well. And so these are some of the things that we really think about that sets MyST and the Jupyter Book ecosystems apart, is that we think about content as structured data. So it has a well-defined structure. We're able to enhance that reproducibility by maintaining links between where the software is written and being able to incorporate them in the documents that we write and ways that we communicate our work. And things should be extensible so that you can come up with your own ways of authoring content, as well as pulling that content into other documents down the line. And we're hoping that this can become more and more ubiquitous. So we're thinking about how this fits into the whole life cycle of knowledge creation and the tools that we work in, both in terms of Jupyter Lab or VS Code or any sort of text editor, and working all the way downstream to the ways that we publish this work with societies, for example. And the community is an open community, it's stakeholder governed, it's part of the Jupyter project. And so we're really leaning into those ideas that have been talked about throughout the sessions this morning in terms of inclusive and participatory team dynamics. And so in terms of some of the superpowers that this gives MyST, this idea of content as structured data, if you go to any of the documentation sites that MyST creates, so mystmd.org, and you add a .json at the end of it, you can see the structure of the document, not just as rendered as HTML, but actually see the data as content behind the scenes. And that includes things like attribution, licensing, authors, and things that are very, very important in the scientific ecosystem of ways to pull in that data, reproduce, and cite that work. And so just writing in this relatively simple markup content gets you that structured data. And from there, we can take that structured data and create the websites out of it. And we can also export to any number of templates in PDF, Word, LaTeX, and be able to create very professional documents at the end of the day, again, based on that structured data and this idea of single source publishing. And I think another way that this comes to life is the structured content allows you to connect ideas. And so that is things like citations or references to a table. You can see that pop up right away. Clicking on a figure reference shows you that figure in seconds, rather than having to download a different PDF document or go to a different website and scroll to the right place. You can see that information directly in context. And that structured content also allows us to connect with external data. And a lot of these ideas about scholarly databases are out there. Like, for example, DOIs, you can have all of the structured information about the authorship and title and all of the metadata behind that work. And to create a scientific citation in MyST Markdown, all you have to do is paste in the DOI, and then you get the citation. So there's no futzing around with APA citations or that sort of thing. You just paste in the persistent identifier. And that works for things like the ROAR ecosystem, which does the same sort of thing for organizations in research, as well as Wikipedia links or links to GitHub issues or pull requests. You can, again, hover over one of those issues and see that directly in context. Another one of the MyST superpowers is allowing that sort of extensible and semantic syntax so that you can extend this into your own domain. And so very briefly, this is some of how MyST Markdown looks, is you create a code or a Markdown fence with these 3 colons or 3 backticks. And then you define what sort of directive you want. And so this could be something like figure or a call out and admonition. You give it maybe some arguments and options, and then the body content. And so as an example, some alerts, some ways to look at figures, some ways to look at cards. And another superpower of MyST is really being part of the Jupyter ecosystem. And so integrating with Jupyter in a really deep way. And so this example is actually running Jupyter Lite, and this is now directly in your browser. There's no server involved here. And you can get all of these sort of really quite interactive graphs that are building upon the ecosystem of IPy widgets and matplotlib, and you can see all of that work behind the scenes and interact with it in a dynamic way. And of course, MyST is driven by a community. And so you can go to our team Compass and figure out ways to get involved, see how our governance is set up, and ways to join the community and discuss the evolution of these ideas. And so that is a little bit about the MyST ecosystem. So I think it wouldn't be, especially following the other two talks today, I think one of the most important things is figuring out how to make it easy to get started with this. And so you can pip install MyST MD, and then if you have a folder of either notebooks or markdown content, all you have to do is write 4 characters MyST and then hit enter, and then that will have you a guide and sort of get started. Then you'll be up to the races, sort of having a website in there. So I'd like to come back to some of these spheres of knowledge in science and how they connect, and really comparing the mediums of how we communicate knowledge in these ways. And in science today, these are often very, very disconnected. So data and story are often coming together in scientific publishing, but they're not actually connected. So even though there's been this sort of explosion of growth in data and code and research practices, traditional scientific publishing infrastructure really has not kept up. And so a caricature of science communication today is a 2-column PDF with a table of data on its side that you're trying to look at on your phone, and you can't copy the information out of. And this is the way that science feels. This is the way that we experience that connection between data and story. It is so disconnected, and software is just off to the side. And in other disciplines, such as business intelligence dashboards, there's this focus on exploration of data through dynamic, connected charts that are most useful when the context is already well established. However, again, in this context, a lot of the story is left off to the side. So what happens when we bring software and story together? And I think there are very intentional ways to do this, to create connections both between people and between ideas. And if we think about social media, for example, there are these companies out there that really do know the power of bringing together data and software and story in non-scientific ways. But it is nonetheless extremely powerful at connecting people and communities. And so there are some other ways that we could look at connection. So for example, how to connect with an idea. For example, this understanding waveforms and harmonics and building up concepts dynamically and interactively. Or bringing in a little bit more data. As you bring that data into the stories, you can ask new questions. Like this example of the hottest day on record, you can start by choosing the city that you want to start with. And so you can ask the question, where is the hottest day where I am? Bringing that connection to a sense of place. And so this is really an interesting and powerful place to play on how data, software, and story really come together. And that interplay between software and data allows for that exploration. And between software and story, it allows for new types of connections to ideas, to places, between communities. And between story and data, we're starting to get at ideas of comprehension. And at the middle of this is learning and discovery. As researchers in this space, we're playing a game between research and publishing, and there's sort of this intricate dance of supporting ways in which ideas move between these roles. And that requires continuous tools to support that choreography. So working towards new ideas, sharing that insights, communicating discoveries with colleagues and the wider world. But if we come back to sort of reality in where scientific publishing is today, it is not that. It's quite far away from that sort of well-choreographed dance, and that is not how it feels. And when you're submitting a publication to, or a scientific article to be published, there's, in terms of time, submitting to journals costs scientists over $230 million just to reformat to specific journal requirements. Submitting to peer review, you're jumping through 1 to 8 months of time with a 77% rejection rate. And at the end of the day, the best of our system is still often paywalled and static, and it really doesn't connect to that software and data in any meaningful way. And much of this comes down to the sort of history of print being so ingrained and entangled at the center of our mindset of science communication. And that brings this philosophy, again, at the center of how we communicate some of the most important ideas of humanity. This workflow is not, it's completely manual, it's closed, it's inaccessible. Some of the tools that we're starting to build with the MyST Markdown ecosystem and Curvenote are focused at this challenge. So trying to move more automation in place to open up this workflow and to make it accessible to everyday researchers, such that it can actually be used to go all the way from sort of in-progress work to publishing that professionally. So when we connect how we work to how we share, it's really powerful. And so thinking about platforms like GitHub and Wikipedia, they allow for working and sharing in the same place. And I want to draw an imperfect analogy to another discipline of knowledge work, which is software development. And this process that we go through as developers in creating packages and sharing and creating sort of those new ideas or software products, I think we can learn a lot from that process and apply it to the scientific process. And so coming through sort of on the software side, starting with requirements, then you might go through design and start to develop something and then release it out to the world. And that is when you start to get feedback on your ideas. And at that point, that's when you get your actual requirements. And this is called waterfall development, and that has largely gone out of favor towards more continuous ways of working. So not spending upfront time to design, is getting something out as fast as possible such that you can get feedback on that as fast as possible. Because you might actually be working on the wrong thing potentially for many months. And so in continuous development, you're maybe starting with a little bit of planning, going through those same sort of ideas of design, but trying to iterate through this as fast as possible. So you're coding, you're building, you're adding automated testing and bringing a lot of those practices that the pyOpenSci community is advocating. And then releasing that, deploying it, monitoring it, and then starting to go through this process all again. And you want to be going through this as fast as possible. And these continuous loops allow for you to rapidly get feedback and test these ideas against reality so that you are actually building the right thing, getting to that right idea, and getting to the right product or tool in the case of software development. So comparing these methodologies, continuous development versus waterfall development, there have been quite a few studies on this, and one study interviewed 36,000 professionals worldwide and grouped those teams based on their software delivery performance, based on how fast do they recover from incidents, or how fast did they release a new feature, what practices do they use, what's important about how these teams are organized. And specifically, these studies begin and compare the speed of iteration and robustness of these systems. So in terms of speed, comparing these two sort of outliers, the high-performing teams were 46 times faster through the cycle when comparing to those sort of more traditional methodologies. So this checks out, for example, if you're thinking about deploying software in terms of every 6 months and going down to multiple times a day. And then from a robustness standpoint, there's this relentless focus on automation to support continuous testing, integration, deployment, and the change failure rate goes down by 7 times. And so much like riding a bicycle, you need some level of speed to actually improve your agility and ability to stay upright. And that is only true if the system is working and those automated processes are accessible to the researchers themselves. And today there's this massive gulf between how we work and how we share in scientific research. And so when thinking about the existential challenges that face humanity, climate change, pandemics, water security, these challenges demand from science that we improve the ways in which we work and the ways in which we share to really meet this moment. To improve the speed of iteration, the time that it takes to build upon an idea, to get to that next breakthrough, the next insight, the next innovation. To know that the work is robust and reproducible because it is connected directly to that software and data. And I think with these numbers, these are not incremental improvements. These are transformational changes. And this analogy is continuous science, so adopting language and concepts from continuous integration and deployment. And of course, these are not one-to-one, but that sort of transformational nature of these, I think there is a lot to learn from this analogy. And it gives us a tool to think through some of the mechanisms to support continuous processes through automation, rapid feedback on errors, focusing small and rapid change sets to accelerate that feedback from peers. And many of the tools that are being taught on improving documentation, reproducibility, continuous testing that you learn throughout the fall festival at pyOpenSci can also be applied directly to communicating and distributing your science openly. So in science, what does that sort of seamless choreographed dance look like between working and sharing? And so you might also go through some planning, collecting data, analyzing that data, authoring it, and then having tools to automatically release that and check it and make sure that it has appropriate metadata all throughout so that you can get some review from not just your close collaborators, but feedback from the community. And that might actually end up being a versioned published release that you can then refine and go through this process again. And the tools that are largely missing in today's ecosystem are the tools that are focused on that automation. And automation is so critical because it enables iteration and versions and being able to improve an idea in place. So sharing it earlier and that sort of integrated software and data into a clear way that supports reproducibility. And that allows you, or these tools can speak to testing and checking things like metadata or reproducibility of the code, or does that data set exist? And am I actually basing my figures off the latest data set? And really getting to those ideas of publication quality of the artifacts, even early artifacts that you share. And trying in a broader sense to support that seamless choreographed dance between research and publishing. These connections between working and sharing are what allows you to get that rapid feedback to work towards that next idea. And so that you can actually build upon this work as fast as possible. So bringing together software, data, and story, I think is a very powerful idea. So I want to bring some more concrete examples. So what if in our scientific papers, we were allowed to explore data directly? What if we could press a button, spin up computational resources in the cloud, and start to understand the methodologies that people use and really bring some of that exploration to life? And I think this is also getting at an idea of frictionless reproducibility, which is at the core of reuse and building upon other people's work, is you don't have to fight through installation instructions to actually just ask a small idea. And as soon as we start to decrease that gulf between I read something and now I want to actually play with it, that is what allows that sort of reuse and reproducibility, and again, getting to that next idea, standing on the shoulders of giants. And at the center of all of this is learning and discovery. And what if we could really think about this as a lake of open science content and open science commons, so that when we hover over footnotes and dive deeper into research, we can pull out somebody else's figure and go all the way down until we find the data and the software that supports the work. And what if we could integrate computational models directly into the ways that we are communicating, so that having not just these models, but actually not just the computation behind the scenes, but actually changing the narrative of how we're interacting with a scientific paper or an article. And there need to be these continuous pathways to connect research and publishing, and that really requires automation, checks, new tools that focus on that automation and connecting software and data into the narrative that we share. And so one way that we're thinking about these tools is making it as easy as possible, going into a repository, hitting misstart, and getting out a publication-ready example that has all of these links directly there that you can share in another command. And we also need tools for checking and automation and testing. So in this case, typing Curvenote check, you can run tools that publishers run directly before even submitting the work. Or if you want to self-publish that work, ensuring that you have the same sort of robustness that is going on in terms of checking metadata on the other side. So metadata, references, ORCID links, even editorial requirements like article length, or if you've included funding information or data availability statement, these are things that can and should be automated. And I think, especially pulling sort of an analogy back to software, as software developers, we know the difference between going into a repository that has linters and pre-commit hooks and automated tests, and going into a repository that doesn't have any of those standards. And at the end of a pull request, someone comes in and says, oh, actually, we do line lengths of 88 characters. And before you merge, can you actually change all of this? And so those tools of automation actually allow us to get to us as researchers being in control of how we are publishing our work all the way through. And of course, we can still and should be able to get PDF documents out. So here is an example from the SciPy proceedings, which is using Curvenote and MyST to run their entire proceedings infrastructure. And they can be beautiful PDFs as well. And so next, I'd like to go through two case studies. The first is a microscopy journal that Curvenote is working with. This is the Team 1 in Lawrence Berkeley National Lab. It's a 2-story high microscope that records at 120 frames per second, and it outputs data at 480 gigabits per second. And that, for context, is the same global upload rate to YouTube, and that is coming from one camera. And that is often then communicated in a scientific journal, which takes a picture of that, and this static 1.5 terabyte data set is boiled down to a single picture that can be shared in a PDF document. But often you need to be able to share the details, create figures with multiple panels, and zoom into areas with specific details, which is, I think, an uninspiring way to share sort of all of this amazing work that's going on. And so about a year ago, Colin, who's the editor-in-chief of a new journal by the Microscopy Society of America, reached out to Curvenote with the goal of creating a new interactive journal that was showcasing the possibilities of integrating data and software into the microscopy community and sort of taking that to the next step. So this is the Journal of Elemental Microscopy. It has a lot of, again, all of those same sort of metadata pieces that you might expect in a journal. But then you can also go in and start computational resources behind the scenes. You're starting up a binder service from the Jupyter ecosystem. You're integrating those ideas of sort of tuning algorithms and understanding actually what they mean all the way through. And behind this, what we're allowing is people to publish not just their narratives, but their computational notebooks behind the scenes, as well as the environments that are required to run those. And what has been quite interesting in working through these processes with a number of journals and societies and researchers is there's often this very healthy push and pull between having to improve the documentation or the packaging processes inside of the actual software, the scientific software that's being used. So in this case, AbTem was one of the tools that was being used behind the scenes for this elemental microscopy journal. And seeing that happen in tandem at the same time is really at the essence of connecting these two ideas of the work actually happening and the work being shared. So, and it's also, I think, a chance for editors and peers to come in and reinforce best practices of packaging, reproducibility, and software versioning at the time where people are also getting academic credit for their ideas. And so also very similar to the workflows used in the Journal of Open Source Software, there are GitHub integrations which run a series of automated checks, and you can proof all of, so in this case, things like ORCIDs, you can see directly, and it gives you some idea of that metadata completeness before you're actually going to publish. And then it gives you a full preview of your work in this way, including the computational aspects and those sort of on-demand Jupyter instances that are brought up behind the scenes. So aiming, again, for all of those sort of automated, reproducible workflows between the ways that people are submitting and the ways that people are publishing that work. And for these 1.5 terabyte data sets, we should be able to just keep on zooming in to these microscope images and actually see them and actually share in a much more authentic way. It isn't a picture, it's a real visualization of the data that you can zoom all the way into. You can change and sort of interrogate cutoffs and ways to actually see this data directly. And one of the other things that comes out of this is that you're reinforcing data standards because you're improving these community-based tools and reinforcing those ways that people are analyzing and exploring these data sets all the way through the ways that they share, not just the ways that they work. Meet Lindsay Hagee. She is a professor at UBC studying carbon capture and storage and geophysical methods for mineral exploration. And she is trying to design her lab to get at these same sort of incentives that I had faced in my PhD, to try and change those incentives for her lab group to improve the ways in which they approach open sharing data and software and storage, so that when someone graduates, the knowledge doesn't sort of walk out the door with them. We don't lose the connections between all of these critical aspects of science, such that the next PhD student or master's student in a group can actually build upon that work and isn't just left with sort of an uninspiring listicle of 100 PDFs to read. So Lindsay wasn't satisfied with the status quo that was sort of having this decades of work just being a list on a CV with limited ability to tell her own story, the sort of through line throughout her career, and bringing some level of creativity that the research demanded of her. And in her work, her and her team are creating all sorts of interactive apps for visualizing results, interrogating ideas, communicating those apps and visualizations in textbooks and courses that are fully open and reproducible, deploying those course materials to students so that they can get up and running to explore concepts dynamically. And she's also, of course, publishing PDFs and journal articles. Many of those artifacts, however, that she's working on don't really fit the mold of a journal article, and they're difficult to, in quotes, publish. And those sort of interactive widgets that explain a concept or a textbook, blog, notebook, ideas, they have such utility and value with those interactive and reproducible pieces at the core of them. And so Curvenote has been working with Lindsay and her lab group on new ways to communicate her work, providing ways to show off their existing publications, as well as new research stories that are entirely on her lab group website. And those through lines from iterating concepts and ideas over decades. Many of this really isn't possible to pull together from the piecemeal disconnected journal ecosystem, and it doesn't allow you to attach and infuse work with computation and data. And some of the work that Lindsay's doing is publishing textbooks, notebooks, seeing sort of the compendium of work behind the work, and having control and creativity over all of that enables new ways to communicate science. This includes meeting notes, presentations, mini conferences like their symposium that they run, and ensuring that all of that work is archived as well as discoverable. And so because of these new interfaces, new ways of sharing her work, it has also changed the incentive of how her lab group is working and how they are archiving some of the requirements that she's introducing into and encouraging her own lab group to adopt. And that is because she now has an outlet to show off the reproducibility, show off the notebooks, textbooks, notes, all of these things that encourage standards and curating and archiving throughout the group. And those concepts of continuous science and connecting that working and sharing really change the research and publishing avenues that they can go after. And it opens new ways for collaboration workflows to be adopted. And some of the people on this Zoom call, for example, had discovered Lindsay throughout some of the efforts that she was doing. And subsequently, they became collaborators, became students, and extended these practices into their adjacent communities. Practicing continuous open science ideas really opens the door for collaborations and growing the community around these tools. So going back to where we are today. Innovation is not just about a fancy journal article with interactive widgets and going beyond the PDF. It's about connecting software, data, and story with a focus on learning and aligning the work all the way through from societal impact to collective understanding to personal ambition to change a field. From gravity to gravitational waves, each of these discoveries has been monumental. However, in the arc of history, it's not the current scientific theory that we celebrate, it's the scientific process we use to show how that theory can be improved. The ethos and the process of science must be aligned to how we publish and share, iteratively, incrementally, open, transparent, and infused with data and software at its core. Imagine a future where Hooke and Newton were not just rivals, but close collaborators, publishing their ideas faster, more openly, more iteratively. What discoveries would society have unlocked sooner? So thank you so much. I'm Rowan Cockett. I'd love to hear from you if you're interested in some of these ideas. You can reach out on rowan@curvenote.com, or I'm also on the Discord in mystmd.org. Thank you very much.